Yes, dear students, today we are going to discuss about the planetary motion. We are going to discuss as a part of gravitation lecture 3. Planetary motion. So in planetary motion, first we want to discuss some theory about that. So let me discuss about general theory. General discussion. So for example, we are having here an elliptical path here, and this is semi-major axis. Here, sun is there as a foci, one of the foci. And one of the focus, what is there here? Sun is there here. Now, planet will be revolving around that. Like this. Different positions I'm going to capture here. So, planet is revolving like this. So, this distance is called what means here? It is closest distance from planet to the sun. So, this is called what we can call it as means R minimum we can call it as. So, generally what we can call it as means perigee. And this distance can be equal to what means A into 1 minus E. A is nothing but semi-major axis distance, and 1 minus E stands for here eccentricity. This is nothing but basics ellipse concept. And here, if you observe here, no, towards this what will happen? Electrostatic gravitational force. Towards this what will happen? Gravitational force. Towards this what will happen? Gravitational. Towards this, in this case, everywhere what will happen? Gravitational force is occurring here. And this is nothing but center. And from here to here, what we can call it as means this is nothing but R maximum. We can write it here, R maximum. So that distance is called what we can take means A into 1 plus C will get it after calculation. So A into 1 plus C, A is nothing but distance, same major axis from here to here distance, and 1 plus C, E stands for what means eccentricity. We can write it here. So this is nothing but planet mass, which we can tell here. So this will be getting attracted in this direction everywhere. So, and this farthest distance is called what means apogee. Opposite. So generally what will happen means due to gravitational force, net torque should be 0. Net torque should be 0. So whenever net torque equals to 0 means you know that torque equals to R vector cross F vector we know here. So what we can write it, torque equals to RF sin theta. So this value is going to be 0. This value is going to be 0 here. So therefore net torque equal to 0 means what we know here, whenever theta value equal to 0. Fine. So we know that F equal to delta P by delta T we know. If force is 0, delta T equal to 0, then what will happen? Delta P equal to 0 means what we can tell? P final equal to P initial we can tell here. This is general common sense main thing. So what we are having here means torque equal to 0 means delta L by delta T. Now if I compare here, in the place of force what will come? Torque will come. In the place of delta P, delta L will come. If torque equal to 0 means what will happen? Delta L equal to 0 will get it. Delta L equal to 0 means L final minus L initial equal to 0. L final minus L initial equal to 0 means LF equal to L5. So Li equal to Li you got it means we have to understand here angular momentum is conserved under planetary motion. Angular momentum is conserved. So angular momentum is conserved, and what is the magnitude of the angular momentum value here means L by 2m equal to constant. So this is the value which we have to remember here. We need not to prove these all things. This is they will ask you only for JEE, and JEE 2019 direct question they asked us. 4 marks bit this question is. Under planetary motion angular momentum is conserved. How much is that value means L by 2m value should be equal to constant. L by 2m equal to constant means L should be constant. L should be constant means L final equal to L initial we can tell here. Next, so what we can tell here means, so this length of apogee equal to length of apogee. So length of apogee is equal to angular momentum of apogee equal to angular momentum of perigee we can tell it here. So means MA into VA RA equal to M into VP RP we can write it here, perigee. So this same will get cancelled. So VA by VP equal to what we can write it? RA by RP. RA by RP can be written as what here? V minimum divided by V maximum, we can write it. V maximum is nothing but what we can write it here? A into 1 minus E divided by A into 1 plus E. So this A also will get cancelled. Therefore, what will get it here finally? 1 minus E divided by 1 plus E will get it. Therefore, if I conclude here, no, VA by VP equal to what we can write it? RA by RP equal to V minimum divided by V maximum, that equal to 1 minus E divided by 1 plus E, we can write it here. This is a standard relation which we have to remember under Kepler's second law. This is all the theory I'm discussing in introduction only, because these all the points are very important, and where E is nothing but what here? Eccentricity, which we can call it as here. So let me have a once again look here. So we are going to discuss general discussion of planetary motion here. So we are having Sun is nothing but one foci here, and around that one planet is revolving, let us assume. So it's getting attracted by what force? F equal to F equal to G m1 m2 by r square is getting attracted now here, and this distance is called what here? Shortest distance, that is called, so this place is called what? Perigee. This position is called what we can call it as apogee. So this distance is called r minimum, this distance is called r maximum. Whenever planet is close, no, that will take more velocity, so high speed is there, far no, low speed is there, that we'll discuss later. So due to gravitational force, net torque should be 0. This is the condition we have to remember. When net torque equals to 0, how means this angle between these two is nothing but 0. Why? Because so whatever the force acting in this direction, no, so the same direction it's acting. R value and force value both are same. If you observe here, no, so if you observe, so this is a line joining two points, and force also acting in same direction. As a result, what will happen? Theta value going to be 0. Whenever theta is going to 0, torque equals to 0. That's how you got it, because sine 0 is 0, 0 into anything will be 0, torque is 0. So we learned that F equal to delta P by delta T. So delta P equal to 0 means Pi equal to P final. It's not conserved, just I'm giving one example here. Similarly, in the place of force, who will come here? Torque will come. In the place of delta P, delta L will come. Whenever torque equal to 0, delta L equal to 0, L final should be equal to L initial. Therefore, angular momentum equals to conserved, we can tell here. What is the magnitude of conserved value here means L by 2m equal to constant. We have to remember for sure this one value, which is they asked in JEE 2019. And we know that L opposite equal to L perigee, means angular momentum of opposite distance equal to angular momentum of perigee distance. So MA, VA, RA equal to M into VP, RT. MM will get cancelled. VA by VP equal to this RA by what will get it? RA by RP, V minimum by V maximum. So A will get cancelled by substitute that values here, 1 minus E by 1 plus E. And again, I concluded here, those are all the values. So here where E is nothing but eccentricity of the ellipse, which we have to understand. Yes, Nana. Now we are going to discuss about Kepler's laws in planetary motion. Kepler's laws of planetary motion, which we are going to discuss here. So in this first, what we are going to discuss means, first law is nothing but law of orbits, which we know. Law of orbits diagram is nothing but just know what we have discussed in general theory, that diagram will get it. So what does this law states means? All planets revolves around the sun in an elliptical orbit. With sun as one of foci. Means, for example, if you take here, we're having like this one ellipse we are having. Here we are having, this is nothing but origin. So sun is there here, foci. We're considering sun as foci. Now all planets are revolving around this like this. So let us assume this is like planet 1. This is like planet 2. So if you observe, no, these all the planets are revolving around the sun in an elliptical orbit with the sun as foci is nothing but what we can tell first law. So then what is meant by second law? If you want to discuss me, second law is important law. So that's nothing but law of areas. Law of areas, which we can tell here. So what does it states means? An imaginary line, we are assuming one line, imaginary line drawn from sun to the planet sweeps out equal areas in equal intervals of time. Equal areas in equal intervals of time. So if you take here, if you take one diagram here, we're having one ellipse here, semi-major axis, semi-minor axis. So semi-major axis distance, how much we're choosing means here, A we are taking here. And if you observe here, if we assume sun is here. Sun. So this is what we're happening means first, when the planet is going here, if this is sweeping this much area, this is planet position. Let us take A1. And for example, planet is here. Somewhere here. So planet is at which position now? Farthest position. Let us consider this is A2. So what will happen means it should sweep equal areas in equal intervals of time. Means if you observe here, this fellow has to going in this direction, but this object, this is a planet is close to him. So to cover more area, what it has to do means it has to cover more circumference here like this. So it has to cover more circumference. But to cover here more area, what will happen means to equal area also, since this radius is becoming more now here, okay, this side length is becoming more now here. So that's why it can move slowly here. So it can move slowly also, equal area it will cover. Whenever the planet is close here, it has to move faster. Whenever planet is close away, it has to move faster to cover equal areas, we can tell here. So generally what we can tell, according to law, what we can tell means dA by dt should be equal to constant. It does mean A1 by T should be equal to A2 by T. So this is the law which we have to remember here. So equal areas in equal intervals of time. So in same time, same area should be sweep. That's why whenever it is close to the sun, it will go away very speed. Whenever it's away from the sun, it goes slow. So that's why. And this position is closest position is called what we can tell means perigee. Farthest position is called what we can tell means apogee. So what we can write it here means next point. So we can tell that nearest position of the planet from the sun means focus is what we can call it means perigee. Similar way, farthest position of the planet from the sun is called what we can call it as means apogee, which we can call it as apogee. So this position is called what we can tell perigee. This position is called what we can tell apogee. And where it will be having more speed, it will be having more speed here, it will be having less speed here to cover more area in less time. So that's why. So what we can tell here means, so you can tell next point, planet close to the sun will have high speed. Next point, what we can mention here, the planets far away from the sun will have low speed. And one more thing which you mentioned here, L by 2m equal to constant is there, no? That is proved under this law only. L by 2m equal to constant. L by 2m equal to constant means what we can tell here? So we can tell that angular momentum is conserved. dl by dt. So L final equal to L final we can tell now. So this thing, many examples they asked, I told you already in JEE 19 and 18 also they asked. So what we can tell means, therefore, angular momentum is conserved, we can tell here. Angular momentum is conserved. Next, what? Third law. And the third law is also called as what means law of periods. So it explains about the time periods, it explains. So actually what does this law states means? This law states like this, Nana. The square of period of revolution of a planet around the sun is proportional to the cube of the distance between the planet from the sun. Sun means we can tell the semi-major axis distance, Nana. Semi-major axis distance. So for example, we are taking one planet here. For example, we are discussing for elliptical orbit. So for elliptical orbit, if you want to discuss here, no, what we are taking here means we are taking one ellipse here like this, and we are having, excuse me, we are having semi-major axis like this. This is nothing but what we can take center from here to your distance. What we are taking A, and here what is it? One sun is nothing but as a foci there, and one planet is somewhere here. Let us assume. So this is nothing but distance from the sun to the planet, which you can tell here. So, and what we can tell for first, what for this, what we can tell means t square is directly proportional to what we can write means a cube, we can write it here. Therefore, t2 by t1 whole square can be written as what means a2 by a1 whole cube, which we can take here. This is for what? Semi-major. This is for elliptical orbit. Which distance we need to take? Semi-major axis we need to take here. For example, if you are solving for circular orbits, for circular orbits, what will get it means? We'll get a circle like this, Nana. Semi-major axis. And here what is that? Mass of the sun. So surrounded by that, what will be there? Planet will be there here, no? So what we'll get here means, and this fellow is moving with tangential velocity v if you take here, no? So this distance is how much we can take here? Radius we can take, no? R for circle. So what we can tell means here, t square directly proportional to what we can tell? R cube. T2 by T1 whole square can be written as what we can write it here? R2 by R1 whole cube, which we can use relation here. This is for circular orbit. This is for elliptical orbits, which we can choose here. Here we are having t square directly proportional to a cube, t square directly proportional to r cube, right? See, if you remove proportionality, you will get a constant that. So what is that constant means? T square directly proportional to r cube we are having. So t square equal to k times the r cube. That k value, how much will get it means? You will get like 4 pi square GME divided into r cube. This is constant here. So why I given this constant value also here means, so always we won't get ratios calculations only. Sometimes we'll get formula based also, direct formula based. So, and we can find in NCERT exercises 3 to 4 questions we can find based on these formulas. Let me discuss a numerical here. In this numerical, what does numerical says means? The distance of a planet from the sun of a planet from the sun is 5 times the distance between Earth and Sun. The time period of the planet is, options are given like this, Nana. Option A, they told like 5 power 3 by 2 years. Option B, 5 power 2 by 3 years. Option C, 5 power 1 by 3 years. Option D, 5 power 1 by 2 years, which they given here. See, if you observe carefully here, no? So in this question, semi-major axis, another elliptical path. So I'm taking here sun. From here to here, I'm taking R. And this distance, what is revolving means, I'm assuming Earth is revolving. At a distance 5R, who is revolving? Another planet is revolving. We need to calculate time period here. So we know that what we know, T square is directly proportional to R cube. We know, no? T square directly proportional to R cube. So T planet divided by T Earth whole square equal to what we can write now? R planet divided by R Earth whole cube, we can write it here. So if we substitute here, no, T planet divided by 1 year for Earth to how long it will take to rotate the sun, completely revolve around the sun, 1 year, no? RP, that is nothing but 5R divided by R whole cube. 1R will get cancelled. Therefore, T planet square equal to what will get, no? 5 power 3 years will get it here. Therefore, T planet equal to what will get? It will go to the square root, it will become, no, square root can be as 1 by 2. 5 whole power 3 by 2 years, if we can write it here. So which of the following option given is correct means option A is correct for this question, which we can tell answer here. Now we are going to discuss about what means we are going to discuss about geostationary satellites. Nana. Geostationary satellites. Name itself is telling. So geostationary, from Earth, if you see, these satellites looks like what, Nana? At rest. So if you take here Earth here, this is the Earth we are considering. And this plane is which plane I'm considering here means I'm considering equatorial plane I'm choosing here. This plane of the Earth is called what we can take? Equatorial plane. So this is nothing but total mass of the Earth is at center, and this radius is how much we know here, RE. So this is a satellite spot which is revolving at a height of what height means? At a height of 6 RE from the surface of the Earth. Height is nothing but how much? 6 RE from the surface of the Earth. So here satellite is revolving which is having mass m means, and that velocity is how much means? V naught, tangential velocity. Okay. So what is the time period of these geostationary satellites means? Time period of the geostationary satellites means it looks like 24 hours it will come. And height is how much means 36,000 kilometers, not 3,600 kilometers. 3,600 is R, no? So how can you write means this value is 6 RE from the surface, no? From surface of Earth. And these geostationary satellites will revolve in which orbit? Equatorial orbit of the Earth. Equatorial orbit of the Earth. So what is the specialty of these satellites means? If we leave any object in this orbital from the geostationary satellite, so that object will revolve around that with the same time speed. So whatever the spinning is, same time speed. In 24 hours, this Earth is spinning itself. So similar way, this object also within 24 hours, it can come back to the again same position. So how can you conclude this point means? If we drop an object from geostationary satellite, it revolve with same speed of Earth. It revolves with the same speed of the Earth means what will happen means it looks stationary from the Earth. Stationary from Earth. That's why these are called as what means geostationary Earth. Geostationary satellites. We can call it as. So why they looks like rest means these are what will happen if you drop an object from the geostationary satellite, it revolve with the same speed of the Earth. Then it looks like what stationary. For example, let me take one example here. Your friend is moving in this direction with 20 meters per second. You are also moving in this direction 20 meters per second. If you observe your friend now, not surrounding. If you observe your friend now, so that friend looks like to rest at for you people. So that's what we can call stationary now here. So that's why we can call these as geostationary satellites, which we can call here. And this is tangential velocity is there. No, that velocity value if you calculate, no, v naught equal to how much it will comes around to be means 3.1 kilometers per second. So these all the values we have to remember here for solving JEE numericals and CET numericals. We need to remember these all the values. That will help us a lot.